Hello everyone, welcome to the course Structure Analysis. I am Dr.S.Pachaiappan, Assistant Professor, Department of Civil Engineering, Aditya University. So today we are at the lecture number 33. So last lecture we started the introduction to matrix method of structural analysis, and then we discussed what are the definitions and then applications of stiffness matrix method and then flexibility matrix method. So in today's lecture, we are going to see the flexibility matrix method, how to apply this method to the continuous beam to get the bending moment values. From that we are going to draw the shear force and then bending moment diagram. So at the end of the lecture, student can able to apply the flexibility matrix methods to the continuous beams and draw the shear force diagram and then bending moment diagram. So already we discussed enough about the stiffness matrix method and then the flexibility matrix method. So it's a simple introduction, and then we are going to moving towards the numerical problems. Okay. So you know that the flexibility matrix method is a force based method. Also it is called as a compatibility method. So it is a matrix forms of consistent deformation method. So we all studied about the consistent deformation method in structure analysis too. So the another name of the consistent deformation method, if the consistent deformation method is in the matrix form, that is nothing but the flexible matrix method. So as I told in the earlier lecture, the primary unknowns are redundant forces, and the number of redundant forces is equal to the number of degree of static inerrancy. That means in the flexibility matrix method, our first aim or thing is to calculate the degree of static indeterminacy. So to explain the degree of static indeterminacy, I have taken one problem. Let's calculate the degree of static indeterminacy for this. So for that, first of all, I need to mark all types of loadings here. So support A, we are going to have the reaction force RA, and then this support is going to subjected to the horizontal reaction HA. Since it is a fixed support, there is a possibility of moment that is called MA. And you can observe the support B and C, it is a roller support. That means it's not going to transfer any forces horizontally, because horizontally it's free to move. Here you can able to see horizontally it's free to move, but so the only vertical reaction will be there. So we can say this is RB, and we can say this is RC. So now we have marked all the unknown forces. Let's count how many unknown forces are there. 1, 2, 3, 4, 5. Total number of unknown forces are 5. And then what is the condition for degree of static indeterminacy? Number of unknown forces minus number of available equilibrium equation. So the degree of static indeterminacy is 2. What is the 2 represents? We have to consider any two forces as a redundant forces, and then by applying the flexibility matrix method, we are going to compute that. Okay. So in my case, I am going to consider, for example, I am considering this RB is unknown, and then I am considering this RC is unknown. So like that, we can formulate the equation after fixing the redundant forces, and then we can solve it. Okay, so this is the example for the static indeterminacy. Now we will discuss about flexibility coefficients, and directly we will solve the problem. So it is very important to understand what is meant by flexibility coefficients. Okay, so I will give some simple example. We have a continuous beam over here. You can able to see the support A is fixed, and we will say this is B and then C. It's not a support. For example, it's a cantilever beam. It's a cantilever beam. In this cantilever beam, I am going to apply the unit force in the two locations. One is a location 1, another one is a location 2, where the displacement is measured. For example, you see the deflection at location 1 due to unit load at the location 1. Where is the location 1? This is the location 1. So deflection at location 1 is nothing but the D1. due to unit load at location 1 itself. Let's give some name for that, that is A. And then the deflection at location 1, so this is the location 1, this is the location 1, due to unit load at the location 2. So you can able to see that unit load at the location 2. Okay. How it is simply understood? What we are going to do, the overall deflection is, let's say it's a D1. We are going to add two values. First, what I am doing, I am applying the unit load at the location 1, and then I am measuring the displacement at location 1 and then location 2 also. At second, what I am doing, I am applying the unit force in the location 2. I am measuring the displacement in location 2 as well as the location 1. So, that is what written here. For example, let us see. The deflection at location 1 due to unit load at location 1 is A. The deflection at location 1 due to unit load at 2 is B. So, and then similarly, the deflection at location 2 due to unit load at location 1 is C, and deflection at location 2 due to unit load at location 2 is D. Now, this D1 is nothing but the summation of A plus B, and then D2 is nothing but summation of C plus D. So, that is what I have written clearly here. What is A represents, what is B represents, C and then D. So, from this we can able to derive the flexibility coefficient. For example, this displacement magnitude A is written as F11, and then B is written as F12, C is F21, D is F22. Now, what is this 1, 1, 2, 2 and all? You can able to see the first subscript of the 1, the first subscript of the 1 represents where we are measuring the deflection. Okay, the first subscript of the letter F represents where we are measuring the deflection. And then the second letter of the F represents the location of the unit force. Okay, so the second one represents the location of unit force, and the first one represents the where we are measuring the deflection. So, it's about where we are applying the unit force and where we are measuring the deflection. So, here also have clearly written what is D1 and what is D2. Then D1 is nothing but F11 plus F12, and D2 is nothing but F21 plus F22. Okay. So, which is multiplied with the force value P. P is a force here, PQ is a force, and we are multiplying with the displacement coordinate. Now, that is what about the flexibility coefficients. Now, we are going to see a numerical problem, how to calculate the redundant forces by using the flexibility matrix method. So, for this problem, I have taken the fixed beam which is having the UDL only the portion of the beam. Step 1, we know already I told we need to calculate the degree of static indeterminacy. As you know, the fixed beam is going to have 3 forces. One is horizontal, another one is vertical, and then moment. But here you can able to see I never consider the value HA. I never considered it. The reason I never considered it means because we consider the beams are axially rigid, and then we are not much worried about the horizontal forces in the beam. We may be worrying about the horizontal forces in analysis of portal frames and then analysis of trusses, but it is not about the beam. Okay. So, if I am not considering the horizontal reaction, then my number of equilibrium equations also reduced 3 from the 2. Okay. So, you know the number of equilibrium equations are 3. If you are not considering the horizontal forces, the number of equilibrium equations are 2 alone. Okay. To avoid confusion, what I am going to do, you consider the horizontal reaction also. So, here 3 forces will be there, here 3 forces will be there. Okay. So, what is the degree of static indeterminacy? Static indeterminacy is equal to number of unknown forces, 6 minus, now number of equilibrium equations are 3, so it will become 3. But in these three, you know that one of the force is nothing but horizontal reaction. If you eliminate that, then it will become 2. So that's what written here. Available equilibrium unknown forces are 4, excluding the horizontal reaction, and then the equilibrium equation is 2, so it became 2. So we are going to fix 2 are the unknown forces. It's our wish actually. I can consider MB and VB as an unknown force, then it will become a cantilever beam. I may also consider the MA and MB is unknown, then it will become a simply supported beam. So we have the, we can able to choose. We have no restraint to choose which is unknown. So in our case, I have taken MB and MC are the redundant forces. So here you can able to see it, MB and then MCR we are considering as a redundant forces. Let's go and yeah, we are considering MB and RB as a redundant forces. So considering MB and then RB as a redundant forces. Now whatever the forces we consider as a redundant forces, we need to remove from the structure. That structure is called as a released structure. So this is the released structure. You can able to see here. Here the fixed support was removed. Here the fixed support was removed, and then we removed the support condition and the moment also. Now where we are removed the redundant force, in that location we need to apply the 1 unit force. That is this diagram. Where we removed the moment, in that location we are going to apply the 1 unit moment here. So let's clearly see, M diagram consists only loads on the released structure. So you see, this is a released structure. The M diagram you see, this is a released structure. Only it is comprises of the load, and we removed the whatever the forces we are considered as a redundant. Now M1 diagram consists of first unit force in the direction of first redundant force. So we considered RB is a redundant force in the location of where RB is acting. In that location, I put 1 unit force. And also, we are removed the MB here, and then where I removed the MB in the same direction, I applied the 1 unit force. So this is the M2 diagram. So it's very simple. You consider some loads or moment as a redundant as per the static inerrancy. According to that, we are going to remove that forces, make the released structure. In the released structure, where you remove the forces, there we are going to apply the 1 unit force or 1 unit moment. Now, this is the equation for the flexibility matrix method. So I have written everything clearly. The D suffix R represents displacement at the redundant forces. For 2 degree of freedom, for 2 unknowns, it is written as dr is equal to 0, 0. Displacement at redundant forces. Displacement at redundant forces means what? We considered support B as a redundant force. Okay, support B, one vertical reaction and moment is acting, that is considered as a, that we consider as a redundant forces. Now, in support B, any support settlements are there? Since there is no support settlement, the displacement at redundant forces are 0. That's what written here. And then DRL represents displacement in released structure due to the given load. Okay. And then F, you know that it's a flexibility matrix method, and then R is nothing but our redundant force. So R is, we considered RB as a redundant force, and then MB is a redundant force. Now, what about the DRL displacement in the released structure due to the given load? This cannot be a 0 because load is there, we need to calculate it. So, from this what we are doing, so this is the actual beam and this is the released beam. So, this is the released beam, and this is the M1 diagram and this is the M2 diagram. What is the M1 diagram? Where we released the first redundant force, there we are applying the 1 unit force. Where is the M2 diagram? What is the M2 diagram? Where we released the moment, in that location we are applying the 1 unit moment. So totally we have M is the released structure, M1 is the first redundant force, we are representing 1 unit force, and then the M2 is the where we removed the second redundant, there in that location we are applying the 1 unit moment. Now coming to this table is very important in the flexibility matrix method. I am going to split this beam into two halves. One is A to C and then C to B. I consider this point is my reference point, so that from here to here the 2 meter distance. So let's take the part B to C, origin I am considering B, and then let's take the part C to A, origin I am considering B. Now I am going to calculate the moment by using the M diagram, M1 diagram, M2 diagram, and then limits. You know, from the B to C the distance is 2 meters, 0 to 2 meters. From the point C to A the distance is 2 to 5 meters. So these are our integration limits. Now coming to the M diagram. So in the M diagram, in between the portion C to B, there is no loading. That's why we have the 0 value. And then when you are talking about, let's clear all the pen marks once. Now what about the M2 diagram? Here 1 unit force is acting, multiplied by the linear distance is x. How it is rotating? Anti-clockwise direction it is rotating. Anti-clockwise means positive. So 1 into x, x. We already completed 0. And then M2 diagram, you see, we are having 1 unit moment. Here you should not do the force multiplied by the displacement, because whatever the redundant we are considering, that itself a moment. So directly 1. Okay, so that itself 1. So we completed all these 3 values. What about the portion C to A? So this is the portion C to A. What is the limit? 2 to 5 meters. So let's see the diagrams. First M. In this portion M diagram, you can able to see from here to here the loading is there. What is that load? 20 kilonewton is there. Now you can able to see, I'll write it here. So 20 kilonewton multiplied by the linear distance is, what is the linear distance? Where it is acting? It is acting the distance of x minus 2. Because you can see our section is here. You can see our section is here. From here to here it is considered as a x. And then what is about this distance? This distance is nothing but L minus x. That's why, so minus of 20 multiplied by x minus 2 is the distance where the UDL will act at the center. So we can say this is multiplied by x minus 2 by 2. So that's what written here. And we can simplify this 2 and 20 if you cancel will be getting minus 10. So that minus 10 into x minus 2, the whole square we are getting. Let's elaborate it. What is this? A minus b, the whole square formula. A square plus a square, this is b square, and then this is minus of 2ab. So this value only is written here. Okay. So this is about the M diagram, and then M1 diagram you can see. So this is the M1 diagram. What you are seeing is the M1 diagram. So 1 into x, and you can see 1 unit moment is there. We no need to multiply with the perpendicular distance. So 1, and the limit is 2 to 5. Okay. So from this way we can segmentally take the continuous beam, and then we can calculate the different moments in the released structure, M1 diagram and M2 diagram. Okay. Next what we have to do? We need to put it into the equation. For example, already I told DRL is represents displacement because of the given loading condition. So how many redundants are there? Here also we need to take it portion wise from B to C and then C to A. Okay. From the B to C you can able to see. From the B to C, the origin is B. What we are supposed to substitute here? We need to substitute the M value and then M1 value. M value is 0. Multiplied by M1 also 0. That's why here we have the value 0. Now what about the remaining things? Here also for the portion of CA, this is the M value and this is the M1 value. So that's what written here. And then we are integrating 0 to 5. This 10 and this 10 I am taking outside, and then EI also I am taking outside. So minus of 10 by EI is taken outside, and then this is the equation. Integrating and then substituting the upper limit and minus lower limit will be getting this value. Similar way we are going to do it for the M multiplied by M2 also. I am getting DRL2 is minus 90 by EI. Now we need to compute the flexibility matrix coefficients. So already we derived F11, we derived F11, F12, F21, F22. We need to compute this value. What is F11? F11 is nothing but M1 multiplied by M1 for the portion B to C. You can see what is the M1 multiplied by M1? X multiplied by X. Okay. So that is the equation. So X multiplied by X. Here you can able to see X multiplied by X. Similarly, this is the for B to C portion and this is for C to A portion. Similarly, we are substituting the value of M1 multiplied by M1 for the portion, both the portion. So finally, we will be getting 41.67 by EI. Now similarly, we will calculate F12 or F21. I told that this is a symmetrical matrix. So F12 is equal to F21. What is that value? M1 multiplied by M2. You see what is mean by M1 multiplied by M2. The M1 value is X, M2 value is 1. That means X multiplied by 1. X multiplied by 1. So for both the portion, X multiplied by 1. And then what is F22? M2 multiplied by M2. Let's go back to the table. M2 multiplied by M2 is nothing but 1 multiplied by 1. So you can able to see 1 multiplied by 1. This is a very simple integration. Even you can able to do it in the calculator also for time saving in the examination. So I got the value 12.5 by EI and then 5 divided by EI. So finally we arrived at the flexibility coefficients. All values need to be substituted back to the general equation. So this is the dr. I told what is the dr? Dr is the displacement at the redundant force. Since we don't have any support settlement, there won't be any displacement possible, 0. And then DRL I told that is the displacement because of the load. So we have a UDL. Because of that UDL, this is the produced displacement 1 by EI, and this is the this is nothing but the flexibility coefficient or flexibility matrix. This is the flexibility matrix, and this is the redundant forces of RB and MB we supposed to calculate. From these I can frame the two equations here. For example, 0 equal to minus of 382.5 by EI plus 1 by EI 41.67. So here you can able to see 41.67 and then plus 12 times of MB. Similarly, we can write the second equation from the matrix form to the equation. Two unknowns. Directly you can able to put it in the scientific calculator and then we'll be getting the value RB value and then MB value. So you definitely can able to understand one thing here. The procedure is highly tedious in terms of flexibility matrix method. Unless like a moment distribution method, Kepler-on theorem of 3 moment method or some other methods, we are going to get this value within 10 minutes. But here it is not possible because these methods are developed for computer programming, not for a manual calculation. Now you see, I can able to see the MB value and then RB value. So the MB value and the RB value I marked in the green color because newly we calculated these values by using the flexibility matrix. But still you can able to see MA and RA is marked in red color because still we don't know that value. So that can be easily calculated now. So I can take a total load is equal to RA plus RB. Since we know the RB value, RA is calculated. So this is also become a green color now. And then taking moment at the point C, okay, taking moment at the point C, I am just calculating this value for drawing the bending moment diagram. So RA multiplied by the distance which we have as 2 meters and then minus 19.78 is the moment acting at the B support. So we will be getting the MC value. Now taking moment at A will give me the moment. So the force multiplied by the perpendicular distance is 5 meters. So this is RA multiplied by the horizontal distance is 5 meters and then minus 19 is the moment over here and then this is the UDL, minus 20 into 3 multiplied by where it will act at center. So 1.5. So how this 1.5 comes? 3 by 2. So equal to MA. So we got the value MA also. This also became a green color now. So we calculated every value by using a flexibility matrix method. Now it is as usual procedure. We are proceeding with the shear force diagram. Since RA RB value is known, I have taken the shear force at A is 44.88 kilonewton, which is nothing but the value of RA. Then shear force at the left of C, you can able to see the UDL is there. So this is minus 20 into 3. And then shear force at the C, this value only we are going to take because at C there is no other values. And then this is the shear force at the B. By using this, we have drawn the shear force diagram. And also we need to locate the point where the shear force is 0. Why we need to locate the point where the shear force is 0? Because where the shear force is 0 at that location we will be having the maximum bending moment. So by computing this X, I can able to draw my bending moment diagram. So you can able to see 44.8 minus 20 into X. How it is came? This is the value of RA. Okay, and then loading is acting in a downward direction. What is that load? 20 into X. The linear distance I know, that's I don't know. That's why we kept at X equal to 0. So from this equation we got the X value. Now what I have to do? I need to calculate what is the bending moment at this point. So we can simply take the moment to that point. So 44 into this X value. This X value we are calculated. Then minus 20 into the X value equal to that X value by 2. So this is X by 2. So we got the bending moment value, maximum bending moment value at the point C. This is MC we can say. Now with this we can able to draw the bending moment diagram. So this is the maximum positive bending moment. This is the maximum positive bending moment, and this is the value of MB. This is the value of MA. Okay, and this is the value of MC. From this we have calculated all the values by using a flexibility matrix method. So you need to pause the video step by step to understand the table. Once you understand the table, remaining things are just a formula substitution and then the basic integration. Okay. So finally, what we have learned from this lecture, we know how to analyze the continuous beam using the flexibility matrix method. Okay. So in the next lecture, we are going to discuss how to solve the problem by using the stiffness matrix method. So thank you for watching this lecture. Thank you.